Welcome to chapter 12. In this chapter, we will talk about the simulation of stochastic processes. So first, we will talk about actually the simulation of the Brownian motion within the Black-Scholes model. So if you remember the stochastic differential equations that we work, basically we are modeling our stock prices using our drift term, and we have the noise term, and we can see that the noise is driven by the increments of the Brownian motion. So the Euler scheme can be utilized for this stochastic differential equation. So we can simply discretize the continuous time derivatives. So you can see that the notation is now using this delta as t. So this is simply the incremental change in the stock price from time t to delta t plus delta t. And you can see that we also discretize the time here, and our Brownian motion is substituted with the standard normal random variable zt times the square root of time. So that this term here exactly follows the distributional properties of the Brownian motion process. And more specifically, within the Black-Scholes model, we have this following equation. And in this stochastic differential equation, we can note that the drift term here, we have this mu, which is constant, and also the volatility term, sigma, is also assumed to be constant in the Black-Scholes model. Although we can actually calculate the analytical solution for the stock price st within the Black-Scholes model, but the simple Euler discretization can also be applied in the similar manner. So, of course, if we use the simple Euler discretization, we can reduce our error, and we can make our discretization better and better by taking smaller time steps delta t. However, obviously, for the Black-Scholes model, we can actually get the analytical solution by applying the Ito's lemma. So we can actually get rid of the discretization error that we see in the Euler's method. So if we actually want to use the analytical solution, we can actually solve the stochastic differential equation for st plus delta t, and actually use the analytical expression to do our simulations. So there are basically four defining properties for the Brownian motion process, because remember here we can use this analytic solution in our simulations, for example, for option pricing purposes. And in order to do that, we need to understand first what are the main properties of the Brownian motion. And you can see that Brownian motion, we are talking about here the one-dimensional standard Brownian motion. It always starts at 0. We have the independent increments property. We have the distributional normality of these Brownian motion increments. So Wt minus Ws is normally distributed with mean 0, and the difference is the difference in time, t minus s. So the variance is t minus s, and t goes to Wt with probability 1. So that's a continuous function on the domain 0 to the capital T. So next we will see the first method to construct the paths of the Brownian motion process.